Tonight, we're going to look at images from the James Webb Space Telescope pictures that feel immediate, detailed, and almost familiar, and recognize that our intuition about what we're seeing is incomplete. You've seen these images before. They look like photographs. They look like moments captured in time. But here's what most people don't realize: almost everything your brain associates with the word image is quietly failing here. Not because the images are misleading, but because the process behind them does not fit human-scale experience. To anchor this, we need scale immediately. The light in these images did not travel across a room, or across a city, or even across a planet. It crossed distances so large that human history fits entirely inside the travel time of a single photon. Civilizations rose, languages disappeared, an entire species vanished while that light was already on its way. When it finally arrived, it did not arrive as a picture. It arrived as an accumulation of signals that could not be seen, could not be felt, and could not be interpreted without machinery built specifically to replace our senses. By the end of this documentary, we will understand exactly what these images are and what they are not. We will understand what is directly observed, what is reconstructed, what is inferred, and where interpretation quietly enters. Most importantly, your intuition will no longer treat these images as distant photographs or artistic renderings, but as precise interfaces between physical reality and human limitation. If you want more long-form explorations like this, you can subscribe. It helps keep this work going. Now let's begin. What we call an image usually begins with a simple assumption. Light reflects off an object, enters our eyes, and forms a picture that feels direct. There may be distance involved, but the chain from object to perception feels short and trustworthy. A tree is there. Light bounces. We see it. The delay is so small that we ignore it. Our intuition treats seeing as almost the same thing as touching. That intuition survives cameras with little damage. A lens replaces the eye. A sensor replaces the retina. The result still feels immediate. Even when we know there is processing involved, the mental model remains stable. The camera points. The shutter opens. A picture is taken. Time feels frozen. Reality feels captured. This is the intuition we bring with us when we look at images from the James Webb Space Telescope. And it is the intuition that fails first. Because nothing about this process resembles light bouncing off a nearby object and entering an eye. The light did not begin near us. It did not travel quickly in human terms, and it did not arrive in a form that could ever be called a picture. We need to slow this down until the familiar breaks. When we say the light traveled for billions of years, that phrase feels informative but weightless. A year is something we schedule around. We divide it into months, days, hours. Billions of them collapse into a word that fits neatly into a sentence. So instead, we replace the unit. Imagine a single human lifetime, not a historical era, not a civilization, one life, from birth to death. Now imagine stacking those lives end to end in time, without overlap, not thousands, not millions, hundreds of millions of complete human lifetimes passing one after another. The light in these images was already moving before the earliest of those lives began, and it did not stop moving until now. During that entire span, nothing about the destination mattered. The photon did not know there would be a telescope. It did not know there would be observers. It moved through expanding space, stretched by that expansion, its wavelength slowly changing as the universe itself changed shape. What finally arrived was not the same light that left, in the sense our intuition expects. It was altered by time itself. This is the first place where the word image becomes unstable. What arrived at the telescope was not visible light in the way our eyes define it. Our eyes are tuned to a narrow slice of the electromagnetic spectrum, because that slice was useful for survival on one planet around one star. The James Webb Space Telescope is not tuned that way. It is tuned to infrared light, much of which has no direct human analogue. There is no colour for it, There is no brightness for it. There is only energy arriving at specific wavelengths. So when the light finally reaches the telescope, nothing like a picture appears, no scene forms, no shapes emerge. Instead, individual photons strike detectors designed to respond not with vision, but with measurable electrical changes. Each photon contributes a tiny increment to a growing data set. This happens slowly, not because the telescope is inefficient, but because the signals are weak. We are not dealing with a flood of light, we are dealing with a sparse arrival, photon by photon, over long periods of time, minutes, hours, sometimes days. The telescope does not take a snapshot, it accumulates evidence. This accumulation matters because it already breaks another intuition. A photograph feels instantaneous. The James Webb Space Telescope produces images that are the result of extended exposure. Layered over time, what we eventually see represents a summary of many arrivals, not a single moment. Time is already smeared before any human sees anything. Now we introduce another scale shift. Each detector on the telescope does not record a picture element in the way a pixel on a screen does. It records a count, a measure of how much energy arrived in a particular wavelength range at a particular location on the detector. That count has noise, it has uncertainty, it is affected by temperature, by cosmic rays, by the behavior of the instrument itself. So before there is an image, there is correction. We subtract signals that do not belong to the object. We account for known behaviors of the detectors. We compensate for distortions introduced by the optics. None of this is optional. Without it, the data is unusable. But each correction moves us further away from the intuition of a direct photograph. At this point, it helps to pause and restate what we now understand. No one has seen these objects directly. No eye, human or mechanical, has ever received a ready-made picture from them. What exists is a record of interactions between ancient light and modern instruments, stretched across time and processed to remove everything we know does not belong. Now we face the question that most people quietly assume has already been answered. If the telescope does not see colour, why do the images have colour? This is where intuition tends to collapse completely, because colour feels fundamental. It feels like a property of objects themselves. But colour is a translation. Even in human vision, colour is a mapping between wavelength and neural response. Outside that narrow range, the mapping simply does not exist. The James Webb Space Telescope detects wavelengths beyond human vision. To make them interpretable, we assign colours, not arbitrarily, but deliberately. Shorter infrared wavelengths may be mapped to blues, longer ones to reds. Sometimes multiple filters are combined, each assigned a different visible colour, so that structure becomes distinguishable. This is not deception, it is interface design. The goal is not to show what the object would look like to a human eye, because that question has no answer. The goal is to compress high-dimensional data into a form the human brain can work with. The colours carry information. They encode differences in wavelength, temperature, composition, but they are not colours in the way a sunset is red. This distinction is critical, and we repeat it until it settles. The image is not a window, it is a map. It is not what is there. It is a translation of what is there into a space where human intuition can operate at all. If this still feels abstract, we return to scale. Imagine trying to represent the entire sound spectrum on a single musical staff. You would have to compress frequencies far beyond hearing into notes that exist only to show relationships. The notes would not be sounds. They would be symbols standing in for something inaccessible. That is what colour is doing here. Once we accept this, another layer becomes visible. Choices are involved. Scientists choose which wavelengths to include. They choose how to map them. They choose contrast levels that reveal faint structures without overwhelming bright ones. These choices are constrained by physics and instrument limits, but they are still choices. This does not make the images subjective in the everyday sense. It makes them conditional. They depend on clearly stated parameters. change the parameters, and the image changes not because reality changed, but because the interface did. At this point, many people feel a subtle discomfort. If the images are processed, mapped, and adjusted, are they still real? We answer this carefully, because the question itself contains a hidden assumption. It assumes that reality must be directly visible to be real. But most of modern science operates where direct visibility is impossible. We do not see electrons. We do not see magnetic fields. We do not see space-time curvature. We detect effects, measure patterns, and build models that survive repeated testing. The images from the James Webb Space Telescope belong to this category. They are not artistic impressions. They are not guesses. They are structured summaries of measured data, constrained by physical laws and instrument behavior. Their reality lies not in their resemblance to human vision, but in their reproducibility and consistency. We can pause again and restate what now holds. The telescope does not take pictures. It collects signals. Those signals are corrected, combined, and translated into images designed to carry information, not familiarity. The result feels visual, but its purpose is analytical. This understanding stabilizes us for what comes next, because once the intuition about images is replaced, we can begin to examine how much of what we think we recognize is actually learned pattern recognition operating on a carefully constructed interface. And that is where the deepest misunderstandings usually begin. Once we accept that these images are interfaces rather than windows, another intuition quietly asserts itself, even if the colors are assigned and the data is processed. The shapes still feel familiar. We see spirals and clouds and points of light. We recognize structure. Our brain treats this recognition as confirmation that we are seeing something directly. This is where the next failure occurs. Human pattern recognition evolved to operate under severe constraints. We are extremely good at detecting edges, contrasts, symmetry, and repetition. This ability is so strong that it activates even when the patterns are not there. We see faces in clouds. We infer motion from static images. We complete shapes that are only partially drawn. Under normal conditions, this is useful. Under extreme scale and indirect observation, it becomes unreliable. The images from the James Webb Space Telescope are designed to be readable by that pattern recognition system. They have to be. Without that, they would remain arrays of numbers, but the moment they become readable, the brain begins to overreach. It starts filling gaps, assigning boundaries, and interpreting gradients as physical surfaces. To understand where this becomes dangerous, we need to separate three layers that are usually compressed into one: what was detected, what was reconstructed, and what was inferred. What was detected is the simplest layer, but it is also the most alien. Individual photons arrived at detectors, producing electrical signals. Those signals were counted, calibrated, and corrected. At this level, there are no shapes, there are no objects. There is only spatially organized intensity across wavelengths. Reconstruction comes next. This is where those counts are arranged into a grid that corresponds to positions on the sky. Distortions from the optics are corrected. Multiple exposures are aligned and combined. Noise is reduced. Resolution is enhanced within known limits. Still, even here, there are no galaxies or stars, only structured variation. Inference arrives last, and this is where intuition quietly takes control. When we say galaxy, we're no longer describing a measurement. We're applying a model. The model connects certain patterns, brightness distributions, spectral signatures, shapes to physical systems we believe exist. The image supports the model, but it does not contain the concept itself. This distinction matters because images encourage us to collapse these layers. We talk as if the telescope saw a galaxy. In reality, it detected light, reconstructed a signal, and allowed us to infer a galaxy through a framework built from decades of prior observation and theory. Now we introduce another constraint that the brain tends to ignore: resolution. The The James Webb Space Telescope has extraordinary resolving power, but it is not infinite. There is a smallest angle it can distinguish. Below that, separate sources blur together. Light from neighbouring objects overlaps. Structures that appear smooth may be unresolved clusters. Sharp edges may be artifacts of processing. The telescope's optics impose a characteristic pattern on every point of light it detects. This pattern, known as the point spread function, means that even a single, isolated star does not appear as a perfect point. It spreads into a shape dictated by the mirror geometry and wavelength. This shape repeats across the image, quietly imprinting the instrument's signature onto the data. Once you know this, you can't unsee it. Spikes around stars are not physical beams shooting through space. They are diffraction effects, predictable and repeatable. They are real in the sense that they are measured, but they are not properties of the objects themselves. This is another place where intuition needs replacement. We're used to treating visual features as belonging to what we see. In these images, many features belong to the instrument. We restate what now holds. The image is a mixture of external reality and internal response. The two are not separate in appearance. They are separated only through analysis and modelling. This separation becomes even more important when we consider faint structures. Much of what makes these images remarkable lies near the limits of detection. Subtle gradients, barely distinguishable from noise, are amplified so they can be studied. This amplification is controlled, but it is still amplification. Choices are made about thresholds, smoothing, and contrast. If this sounds like distortion, we slow down. The alternative to amplification is invisibility. The universe at these distances does not present itself loudly. It whispers. If we demand unprocessed purity, we learn nothing. If we process without discipline, we invent structure. The balance is maintained through reproducibility. Different teams, using the same raw data and similar methods, arrive at consistent results. This consistency, not visual realism, is what anchors trust. At this point, it helps to return briefly to human experience, not as an analogy to reuse, but as a calibration. Imagine trying to understand a city at night from an airplane window. Individual lights blur together, roads appear as glowing lines. You infer neighbourhoods, not because you see houses, but because you recognise patterns of density and arrangement. The inference is reliable, but it is not direct. The images from the James Webb Space Telescope operate at a similar remove, but across scales that remove any possibility of direct verification. We cannot travel to these objects. We cannot observe them from another angle. The image must carry enough information to support inference on its own. This is why spectral data is inseparable from imaging. Each region of the image is associated with wavelength information that reveals composition, temperature, and motion. When we say a region is forming stars, that statement rests not on its appearance, but on the presence of specific emission lines and energy distributions. The visual structure is supportive, not decisive. This is another intuition to dismantle. The image is not evidence by itself. It is a coordinate system for evidence. Once this settles, a quiet shift occurs. The question "is this image real?" starts to feel poorly formed. Realness no longer hinges on visual similarity to everyday experience. It hinges on whether the chain from detection to inference is transparent, constrained, and testable. There are limits here, and acknowledging them stabilizes understanding rather than undermining it. There are structures too small to resolve. There are wavelengths we cannot observe simultaneously. There are assumptions embedded in every model. None of these are hidden. They are documented, debated, and revised as instruments and methods improve. We pause again and summarize what we now understand. The images are not snapshots of objects as they would appear to an observer floating nearby. They are structured representations of measured light, shaped by instrument physics, processed to reveal patterns, and interpreted through models that have survived extensive testing. This understanding prepares us for the most subtle misunderstanding of all, the idea that greater detail means greater certainty. As resolution increases, complexity increases with it. More structure appears, but so do more opportunities for misinterpretation. The work does not get simpler as the images improve, it gets more demanding. And that is why these images are not endpoints. They're working surfaces, places where observation, reconstruction, and inference meet under carefully controlled conditions. With this frame in place, we're ready to examine how time itself enters the image, not just as distance travelled, but as an active dimension that shapes what can and cannot be known. Time is the next intuition that needs to be rebuilt, because so far it has remained quietly familiar. We have acknowledged that the light travelled for an immense duration, but we have still treated that duration as something that happened before the image existed. Once the image appears, time feels resolved, flattened into a view. That feeling is false. The image is saturated with time. To see why, we return to the moment of detection, but we slow it further. The James Webb Space Telescope does not receive all the light at once. It receives light continuously while it observes. During that observation, the universe does not pause. Objects evolve. Radiation environments fluctuate. The telescope itself moves, cools, and responds to changing conditions. So even before processing, the raw data already represents an interval, not an instant. This interval can last hours or days. During that time, the telescope collects photons that left their sources at slightly different moments. For nearby objects, that difference is negligible. For objects billions of light-years away, it is not. The image blends together emissions that were never simultaneous in any absolute sense. The farther we look, the thicker this temporal layer becomes. This is where everyday intuition breaks sharply. On Earth, when we look at something, we see it as it is now, within a tiny fraction of a second. The delay is irrelevant. With the James Webb Space Telescope, now has no stable meaning. Every region of the image corresponds to a different moment in the past, and those moments can differ by millions of years across the same frame. We repeat this until it holds. The image is not a slice of time. It is a collage of different pasts, assembled according to where the light happened to originate. Once this settles, another layer of time appears. The universe is expanding. As space expands, light travelling through it stretches, its wavelength increases. This process does not stop when the light is emitted. It continues for the entire journey. By the time the light arrives, its properties encode the history of that expansion. This means that wavelength is not just a marker of energy, it is a marker of time. When the James Webb Space Telescope detects infrared light from extremely distant objects, it is not because those objects emitted infrared light to begin with. Many emitted visible or ultraviolet light that was stretched into infrared during transit. So when we assign colours to these wavelengths, we are indirectly encoding temporal depth. Redder regions often correspond to earlier cosmic times. Bluer ones correspond to later ones. The image quietly becomes a time map. This is not an artistic choice. It is a consequence of cosmology. But it is another place where visual intuition misleads us. We are not seeing different colours of the same moment. We are seeing signals from different epochs, compressed into a single spatial arrangement. At this point, we pause and restate. The image blends time in three ways: the duration of observation, the varying light travel times across space, and the stretching of wavelengths due to cosmic expansion. None of these are visible as time. They are encoded in intensity and colour. Now we confront a subtle assumption that often goes unnoticed. When we see structure arms of a galaxy, clumps of gas, we tend to imagine them as stable entities, frozen long enough to be captured. But many of these structures are transient on cosmic timescales. They form, evolve, and dissipate over millions of years. the image does not show them evolving. It shows a single composite representation drawn from light that left at different stages of that evolution. This does not invalidate the image, it defines its limits. To understand how scientists work within these limits, we look at repetition. The same region of the sky is observed multiple times, sometimes across different wavelengths, sometimes years apart. Changes are tracked, models are updated. The static image becomes one frame in a slow-motion sequence that spans decades of observation and billions of years of inference. This is why no single image stands alone. Each is a node in a network of data. Its meaning depends on how it aligns with other observations and predictions. Now we introduce another temporal constraint to the telescope's own lifespan. The James Webb Space Telescope operates under finite conditions. Its fuel is limited, its instruments age, its configuration is fixed. Every observation is made under these constraints, and future observations may not be able to repeat them exactly. This introduces urgency, but not drama. It simply means that the images we have are products of a specific moment in technological capability. They represent the best interface we can currently build between ancient light and human understanding. We rest again. Time is not something the image escaped. It is something the image carries. Once this is accepted, a new question emerges naturally, without forcing it. If the image blends different times, how do we compare distant objects to nearby ones? How do we build a coherent picture of cosmic history from fragments that were never synchronized? The answer lies in models that explicitly include time as a variable. Distances are converted into look-back times. Redshifts are translated into epochs. Populations of objects are grouped not by proximity, but by inferred age of the universe when their light was emitted. This process is careful and constrained. It relies on well-tested relationships between redshift, expansion rate, and cosmic parameters. It also carries uncertainty. Measurements have error bars, models have ranges. None of this uncertainty is visible in the image itself. This is another reason the image cannot be treated as a photograph. A photograph suggests completeness. These images are partial views embedded in probabilistic frameworks. We slow down again and repeat what now feels stable. The James Webb Space Telescope images do not show the universe as it is, or as it was at a single moment. They show structured evidence of processes unfolding over vast spans of time, compressed into a form that can be analysed visually. At this point, the original question, how real are these images, has shifted. Realness is no longer about immediacy or simultaneity. It is about whether the temporal distortions are understood, quantified, and accounted for. They are. But acknowledging this opens another layer that intuition still resists. If time is encoded and blended, and if interpretation depends on models, then where exactly does certainty live? What parts of the image are direct consequences of measurement, and what parts depend on assumptions about how the universe behaves? To answer that, we need to examine how models constrain what the image can mean, and how those constraints prevent imagination from running ahead of evidence. That examination begins by understanding why older models once made sense and why they had to be replaced. To understand how interpretation is constrained, we need to examine the frameworks that make interpretation possible at all. These frameworks did not appear fully formed. They were built gradually, under conditions where the universe looked simpler than it does now. Older models were not naive. They were efficient responses to limited evidence. Early astronomical models assumed stability because stability was what observation allowed, when instruments could only resolve nearby stars and galaxies. Change was slow and difficult to detect. The universe appeared largely static on human timescales. Light arrived quickly enough that time delays could be ignored. Distance and age felt loosely connected, not causally locked together. Within that context, it made sense to treat celestial objects as enduring structures. Galaxies were classified by shape. Nebulae were categorized by appearance. The models worked because the observations did not yet demand more. But as instruments improved, cracks appeared. Some objects did not fit neatly into categories. Spectral lines shifted. Distant galaxies looked systematically different from nearby ones. These differences were not random. They followed patterns that could not be explained by static assumptions. This is where models began to absorb time as a central component. Distance stopped being just a measure of separation and became a measure of look-back. Redshift stopped being an oddity and became a clock. The universe transitioned from a collection of objects to a system with a history. The James Webb Space Telescope operates entirely within this modern framework. It does not ask whether the universe changes. It assumes change and measures its consequences. This assumption matters when interpreting images. When we see a distant galaxy with irregular structure, we do not default to poor image quality. We consider that we may be seeing an early stage of galaxy formation. That interpretation rests on models of how galaxies evolve over billions of years, constrained by simulations and prior observations. These models are not decorative. They are mathematical structures built to satisfy multiple independent constraints. They must reproduce the large-scale distribution of galaxies, the chemical composition of stars, the background radiation of the universe, and the observed expansion rate. An image that contradicts these constraints is not accepted quietly. It triggers revision. This is where certainty lives not in visual impression, but in consistency across domains. We pause and restate. The image does not dictate the model. The model limits the image's interpretation. This reversal is unintuitive, but essential. Without it, every unusual feature could become a discovery. With it, discoveries are rare and hard won. Now we return to the image itself and ask a narrower question. Which features are model-dependent, and which are directly anchored in measurement? Brightness is one of the most direct quantities. The amount of light detected at a given wavelength, after calibration, is a measurement. Its uncertainty can be quantified. Its variation across the image is real in the strictest sense available. Position is similarly grounded. The location of a signal on the detector corresponds to a direction in the sky. Distortions are corrected, and residual errors are tracked. When we say something is here rather than there, that statement has a clear observational basis. Structure, however, is more subtle. When brightness varies smoothly, we infer extended objects. When it clusters, we infer discrete sources. These inferences depend on assumptions about how light-emitting matter behaves. They are reliable, but they are not raw. Even more model-dependent are properties like mass, age, and composition. These are not seen. They are inferred from spectral features and compared against theoretical predictions. When we color-code an image to represent temperature or chemical abundance, we are embedding layers of modeling into the visual field. This does not weaken the image. It makes it usable. To see why, consider the alternative. Without models, the image would be an uninterpreted pattern. With too much freedom, the image would become a canvas for imagination. The narrow path between these extremes is where science operates. This path is maintained through falsifiability. Models make predictions, images test them. When predictions fail, models are adjusted or abandoned. This cycle is slow and conservative. It favors stability over novelty. The James Webb Space Telescope was designed with this cycle in mind. Its instruments are optimized not just to produce striking images, but to gather data that can discriminate between competing models. Subtle differences in wavelength response, resolution, and sensitivity matter because they constrain interpretation. We rest again. The image is not a claim, it is a constraint. At this point, it becomes possible to address a common misunderstanding without dismissing it. Some people sense that because models are involved, the images are less trustworthy. In fact, the opposite is true. The explicit presence of models makes the assumptions visible. They can be challenged, tested, and refined. Implicit assumptions are far more dangerous. When we treat an image as a direct view, we smuggle in assumptions without noticing. The James Webb Space Telescope forces those assumptions into the open, where they can be examined. This transparency extends to uncertainty. Every derived quantity has an associated range. These ranges are not aesthetic, they are mathematical expressions of what the data allows. When images are released, the underlying data and processing steps are also released. Independent teams can reprocess, reinterpret, and critique. This is another stabilizing point. The reality of the image does not depend on authority or trust in a single group. It depends on the robustness of a shared process. Now we shift slightly, not by introducing a new topic, but by tightening focus. The more distant the object, the heavier the reliance on models. The nearer the object, the more direct the measurement. This gradient is continuous, not discrete. Understanding this gradient replaces a binary intuition, real versus not real, with a spectrum of confidence. Some features are anchored close to measurement, others float further out, tethered by theory. Knowing where a feature lies on this spectrum is part of scientific literacy at this scale. We repeat this until it settles. The image is layered. Some layers are solid, some are provisional, all are labelled. With this frame, we are prepared to examine how public-facing images are constructed from scientific data, and why aesthetic choices do not undermine scientific validity, but serve a specific function in human cognition. Once we understand that images are layered structures constrained by models, the question of presentation becomes unavoidable. The images released to the public do not look like raw data, and they are not meant to. This gap between scientific data and public images is often where trust erodes, not because something is hidden, but because the purpose of the transformation is misunderstood. To rebuild intuition here, we separate function from appearance. The raw output of the James Webb Space Telescope is not visually interpretable in any human sense. It consists of arrays of values associated with detector pixels, each value corresponding to the amount of infrared radiation detected in a specific wavelength range. Viewed directly, this data resembles static or noise. Patterns are present, but they are submerged in instrumental signatures and background effects. Before any scientific analysis can proceed, this data must be cleaned, known detector behaviors are corrected, background signals are removed, artifacts caused by cosmic rays or transient events are identified and excluded. These steps are not optional enhancements. They are necessary to prevent false conclusions. Once this calibration is complete, scientists begin working with the data in forms that are still not images in the everyday sense. They examine plots, spectra, and numerical summaries. Visual representations are tools among many, not the final authority. The images that circulate widely serve a different purpose. They are designed to compress complex multidimensional data into a form that can be apprehended by human visual cognition. This compression requires choices. Those choices are guided by clarity, not deception. Color assignment is the most visible of these choices, and it is also the most misunderstood. We have already established that the telescope does not detect visible color. What matters now is why particular mappings are chosen. Different filters capture different wavelength ranges. Each filter reveals different physical processes. When these filters are combined into a composite image, colors are assigned to represent these differences. The mapping is usually monotonic. Longer wavelengths are assigned redder colors, shorter ones bluer. This preserves relative relationships even if the absolute colors are artificial. The goal is to make differences legible. Without color separation, many structures would overlap visually, indistinguishable in grayscale. Color becomes a labeling system embedded in the image. Contrast adjustment is another essential step. The dynamic range of the data, the difference between the brightest and faintest signals, often exceeds what screens or eyes can display. If shown linearly, either bright regions would saturate or faint ones would vanish. Nonlinear scaling is applied to reveal structure across this range. This scaling does not create information, it redistributes visibility. faint features become apparent at the cost of compressing brightness differences elsewhere. The underlying measurements remain unchanged. We pause and restate. The public image is not a scientific output. It is a translation layer designed to support human interpretation while preserving the relationships that science cares about. This translation layer introduces aesthetic considerations, but aesthetics here serve function. A visually coherent image reduces cognitive load. It allows patterns to be seen without exhaustive explanation. This is not about beauty as an end. It is about efficiency of understanding. Importantly, these images are not the only representations of the data, nor are they the ones used to draw quantitative conclusions. Scientific papers rely on plots, tables, and statistical analyses. The image is a gateway, not the argument. Understanding this prevents a common error assuming that because an image looks dramatic, the science is dramatized. In reality, the drama arises from scale and complexity, not from embellishment. We return briefly to a human-scale calibration. When medical imaging is displayed, colours are often assigned to represent tissue density or activity. No one assumes those colours are what the body really looks like. They are understood as mappings that convey information efficiently. Astronomical images operate under the same principle, but the familiarity is lacking. Once this analogy serves its purpose, we discard it. Now we address a more subtle concern. Could different choices produce different impressions? Yes, and this is why transparency matters. The processing steps, filter choices, and scaling functions are documented. Alternate renderings can be produced from the same data. When these renderings agree on structure despite differing aesthetics, confidence increases. Disagreement is also informative. If a feature disappears under certain processing choices, it may be near the noise threshold. This does not invalidate it, but it flags it for caution. This iterative process, adjusting representation, checking robustness, is part of how scientists interrogate data. The public image is one snapshot of this process, not its conclusion. We rest again. The image is not an assertion of certainty. It is an invitation to analysis. At this point, it becomes possible to explain why the phrase false colour is both accurate and misleading. The colours are not false in the sense of incorrect. They are false only if we assume they claim to represent human vision. Once that assumption is removed, the term loses its sting. A better frame is informational colour. Each hue carries meaning assigned by convention and physics. Learning to read these images is like learning to read a map. Mountains are not brown because they are brown. They are brown because that colour encodes elevation. With this frame, trust stabilizes. The image is no longer pretending to be something it is not. It is openly symbolic, grounded in measurement. This brings us to an important restatement. The James Webb Space Telescope images are real in the same way graphs, spectra, and models are real. They are real because they reliably represent relationships in the physical world, even when those relationships cannot be experienced directly. At this stage, intuition has been rebuilt enough to face a more difficult boundary. Even with careful processing, even with robust models, there are things these images cannot tell us. There are ambiguities that cannot be resolved by better colour choices or deeper exposures. Understanding where the image stops being informative is as important as understanding what it reveals. That boundary becomes visible when we confront the limits imposed not by technology, but by physics itself. Once we reach the limits imposed by physics, intuition faces a different kind of resistance. Up to this point, misunderstandings could be corrected by clarifying process, scale, and representation. Here, the obstacle is not confusion, it is constraint. There are questions the images cannot answer, not because we have not yet learned how, but because the universe does not allow it. To understand this, we begin with resolution again, but this time as a physical boundary rather than a technical one. The James Webb Space Telescope has a finite mirror size. That size determines how finely it can distinguish detail. This is not a matter of engineering preference. It is set by the wave nature of light. Light spreads. Diffraction occurs. Even a perfect mirror cannot focus light beyond a certain limit. This means that below a specific angular scale, structure is irretrievably blurred. Two objects closer than that scale cannot be separated. No matter how long we observe, more exposure time increases signal strength, not sharpness. The information simply is not there. This is a hard stop, and it matters. When we look at distant galaxies, we're often seeing conglomerates of unresolved components. Star clusters blur into smooth regions. Individual stars disappear into collective glow. The image does not contain hidden detail waiting to be extracted. It contains averaged information. This replaces another intuition. We tend to believe that if something exists, enough effort will reveal it. At these scales, effort meets a wall. Now we introduce a second physical limit: opacity. Not all regions of the universe are transparent. Dust absorbs and scatters light. Gas clouds block certain wavelengths. Some processes emit radiation that never escapes their environment, even infrared, which penetrates dust better than visible light, encounters limits. So when an image shows a dark region, it is not always absence. Sometimes it is obstruction. Sometimes the information never left the source. No amount of observation can retrieve what was not transmitted. This is not a gap in our methods. It is a property of matter and radiation. We pause and restate. The image shows what arrived. It does not show what could not arrive. A third constraint comes from time itself. Some processes unfold faster than the observation cadence. Rapid events may blur or vanish when integrated over long exposures. Others occur so slowly that they appear frozen, even though they are evolving. This means that certain kinds of motion and change are invisible. We infer dynamics from static patterns, guided by models. These inferences are often reliable, but they are not direct observations. At this point, it becomes clear that the image is not a complete record of reality. It is a filtered one, shaped by physical law. Understanding this helps us approach uncertainty without discomfort. Uncertainty is not a flaw in the image. It is a map of where physics limits access. Now we consider a particularly persistent intuition that deeper images reveal older truths. This feels natural. Looking farther seems equivalent to looking earlier, and looking earlier seems like approaching origins. But depth does not guarantee clarity. As we look farther back in time, signals weaken, redshift increases, structures become smaller and harder to resolve. Overlapping sources confuse interpretation. The earliest epochs are not pristine snapshots. They are noisy, incomplete traces. This means that some of the most fundamental questions about the first stars, the earliest galaxies, the initial conditions of structure are addressed statistically, not visually. We observe populations, not individuals. We measure distributions, not details. The images support this work, but they do not replace it. We rest again. The farther we look, the more we rely on inference. This is not failure, it is adaptation. Now we address an important misconception directly, without judgment. Some people believe that future telescopes will simply overcome these limits. Larger mirrors, better detectors, sharper images. Some limits will shift, others will not. Diffraction can be reduced but not eliminated. Opacity depends on wavelength but never vanishes entirely. Information that never escaped its source cannot be recovered. These are not engineering challenges, they are boundaries. Recognizing boundaries does not diminish discovery, it focuses it. Scientists design questions that can be answered within these constraints. They do not ask images to deliver what physics forbids. This is why the James Webb Space Telescope is paired with other instruments and methods: radio telescopes, gravitational wave detectors, particle experiments all probe different channels. Reality is reconstructed across modalities, not from a single view. The image becomes one layer in a composite understanding. We pause to consolidate. The images are not incomplete because they are images. They're incomplete because reality itself is not fully accessible from any single vantage point. This realization stabilizes expectation. We stop asking the image to be more than it can be. We start reading it for what it is. At this stage, the phrase "we don't know" begins to acquire a different weight. It no longer signals ignorance. It signals a boundary that has been located, tested, and respected. When scientists say they do not know exactly how certain early galaxies formed, they are not waiting for a clearer picture. They are acknowledging that multiple models remain consistent with the available evidence. The image constrains possibilities without collapsing them into one. This is how progress occurs under constraint. Models compete. Data narrows the field. Some ideas are discarded. Others survive provisionally. The image is active in this process, not passive. It does not provide answers. It eliminates impossibilities. We rest again and repeat what now feels stable. The James Webb Space Telescope images are real, but they are real within a framework defined by physical law. They show what can be shown. They withhold what cannot. With this understanding, we are ready to examine how these images interact with older intuitions inherited from earlier astronomy, and why some lingering misunderstandings persist even among people familiar with the science. Those misunderstandings do not come from ignorance. They come from intuition that has not yet been updated to operate under these constraints. Some of the most persistent misunderstandings about these images do not come from technical confusion. They come from older intuitions that once worked well and have not yet been fully replaced. These intuitions were shaped by centuries of astronomy conducted under very different conditions, and they still quietly guide interpretation, unless they are explicitly dismantled. One of these intuitions is that better instruments simply reveal smaller versions of familiar things. We imagine that as resolution improves, distant galaxies will begin to look like nearby ones, just fainter or more compact. This expectation feels reasonable because it matches everyday experience. A distant building looks like a nearby one viewed from far away. But this intuition fails because the universe changes with time. When we look far away, we're not just looking at smaller images of mature systems. We are looking at systems that exist under different physical conditions. The universe was denser, gas composition differed, star formation proceeded differently. Structures that seem irregular or chaotic are not degraded versions of modern galaxies. They are earlier stages governed by different balances of forces. This is why some James Webb images feel unfamiliar even when they are sharp. The unfamiliarity is not a failure of imaging, it is evidence of genuine difference. Another inherited intuition is that classification precedes understanding. In earlier astronomy, objects were grouped by appearance because appearance was all that was accessible. Spirals, ellipticals, irregulars. These categories were useful and still are, but they are no longer primary. Modern interpretation prioritizes physical processes over visual categories. Two objects that look similar may operate under different conditions. Two objects that look different may share underlying mechanisms. The image alone cannot resolve this. Spectral data and modeling are required. This means that visual similarity no longer guarantees physical similarity. The brain resists this because pattern matching feels reliable. Updating this intuition requires repetition. We pause and restate. Familiar shapes do not imply familiar physics. Another lingering intuition concerns completeness. When we see a detailed image, we assume it shows the whole object. But many structures extend beyond what is visible at any given wavelength or sensitivity. Halos of gas, faint outskirts, and diffuse components often fall below detection thresholds. So when we see the boundary of a galaxy in an image, we are not seeing an edge, we are seeing a limit of detectability. The object continues beyond it in forms that may require different instruments or methods to observe. This is especially important when comparing objects across time. Early galaxies may appear compact not because they were small, but because their outer regions are too faint to detect at extreme distances. interpreting size evolution requires careful correction for these effects. Again, the image constrains interpretation but does not dictate it. We rest again, visibility is not extent. Another intuition that persists is the idea that absence of evidence is evidence of absence. When features are not seen, it is tempting to conclude they are not there. At these scales, this is often unjustified. Non-detection may result from sensitivity limits, wavelength choices, or observational geometry. Scientists treat non-detections carefully. Upper limits are established. Models incorporate them without collapsing possibilities prematurely. This caution is invisible in the image but central to its interpretation. Now we address a particularly subtle intuition that the image represents a single object observed under uniform conditions. In reality, many images combine multiple filters taken at different times and orientations. The final composite merges these into a coherent view. This merging is necessary, but it introduces complexity, slight misalignments, variable conditions, and instrument behavior must be corrected. Residual effects can remain. Experienced analysts recognize these signatures. Casual viewers do not. This does not mean the image is unreliable. It means it must be read with knowledge of its construction. We pause and consolidate. Many misunderstandings arise not from false information, but from applying outdated intuitions to new regimes. Once these intuitions are replaced, something interesting happens. Skepticism becomes more precise. Instead of asking whether the image is real, we ask which aspects are directly measured, which are inferred, and which remain ambiguous. This is a more productive stance. At this stage, we can also address why debates about authenticity sometimes feel circular. One side demands directness, the other explains mediation. Without updated intuition, these positions never meet. Directness is no longer the criterion, constraint is. We rest again. Reality at this scale is accessed through constraint, not immediacy. This prepares us to examine how scientists themselves interact with these images. Contrary to popular perception, they do not treat them as final products. They treat them as provisional representations that invite further interrogation. Images are revisited as calibration improves. Processing pipelines are updated. Earlier interpretations are refined or corrected. This does not signal weakness. It signals a living process. Importantly, this process is slow. Claims are not revised with every new image. Patterns must persist across observations. Independent groups must converge. This conservatism is intentional. Understanding this changes how we view announcements and headlines. A striking image does not imply a dramatic revision of knowledge. It implies an opportunity to test existing frameworks under new conditions. We pause again to stabilize understanding. The images are not proclamations, they are stress tests. With this frame, we are ready to approach a different kind of question, one that shifts attention away from what the images show and toward what they allow us to rule out. This shift marks a deeper level of understanding. At this level, the power of the James Webb Space Telescope lies not in revealing new forms, but in narrowing the space of viable explanations. The images become tools for exclusion as much as for discovery. To see how this works, we need to examine specific cases where expected features failed to appear, and how those absences reshaped models without requiring dramatic reinterpretation. That examination continues by looking at how prediction and surprise interact under conditions of extreme uncertainty. Prediction and surprise interact in a controlled way in modern astronomy, and nowhere is this clearer than in how images are used to test expectations. Surprise does not mean confusion. It means that a prediction, derived from a model, encountered a constraint imposed by observation. The image is where that encounter becomes visible. Before the James Webb Space Telescope began returning data, many predictions already existed. Models of early galaxy formation suggested certain sizes, brightness distributions, and rates of star formation. These models were not speculative. They were extensions of frameworks that had already succeeded at explaining large-scale structure and cosmic background radiation. When the first images arrived, some features aligned well with expectations, others did not. Certain early galaxies appeared brighter or more structured than anticipated. This triggered attention, not alarm. The important point here is that the image itself did not overturn models. It narrowed the space they could occupy. Adjustments were required, but wholesale abandonment was not. This distinction is often lost outside the scientific process, where surprise is equated with contradiction. We slow this down. A prediction is not a single outcome. It is a range. When observations fall outside that range, the model must change. When they fall inside it, even if near the edges, the model survives. Images provide the data points that perform this test. Now we consider how absence functions as a constraint. Some predicted features simply do not appear. Certain populations of objects are rarer than expected. Certain spectral signatures are weaker. These absences are not failures of the telescope. They are information. But absence is harder to visualize than presence. A blank region does not announce itself. It must be interpreted relative to sensitivity limits, exposure time, and wavelength coverage. This interpretation is careful and statistical. For example, if early galaxies lack expected dust signatures, this constrains timelines for chemical enrichment if certain emission lines are weak or missing. This constrains models of star formation and feedback. The image supports these conclusions not by what it shows vividly, but by what it fails to show despite sufficient sensitivity. This is a key intuition replacement. Discovery does not always look like a new shape. Sometimes it looks like an empty space where a shape was expected. We rest and restate. Images test predictions by presence and by absence. This brings us to a subtle but crucial distinction between surprise and anomaly. An anomaly persists across observations and resists integration into existing models. Most surprises do not reach this status. They are absorbed through parameter adjustment. This conservatism is not resistance to change. It is protection against overfitting. A single striking image is insufficient to justify rewriting frameworks that explain many other observations. The James Webb Space Telescope accelerates this process by expanding the parameter space under test. It does not loosen standards, it tightens them. Now we examine how images contribute to exclusion. When certain theoretical scenarios predict features that are not observed across many targets, those scenarios lose viability. This narrowing happens quietly, without dramatic announcements. Papers note reduced likelihoods. Confidence intervals shift. Attention moves. The public image rarely reflects this work directly. It shows a particular object or region, not the statistical landscape, but the image is still the origin of constraint. We pause again. The power of the image lies less in what it reveals to the eye and more in what it forces the model to abandon. At this stage, intuition about certainty needs adjustment. Certainty does not arrive as a visual conclusion. It accumulates as competing explanations are eliminated. Images participate in this elimination. Now we consider another expectation that often goes unexamined, that sharper images produce clearer answers. In practice, sharper images often reveal complexity that blurs interpretation. Structures fragment. Environments appear heterogeneous. Simplifying assumptions fail. This does not weaken knowledge, it refines it. For example, early assumptions about smooth star-forming regions give way to evidence of clumpiness and feedback. Models adapt to include turbulence, radiation pressure, and variable efficiency. The image did not provide the explanation. It forced the explanation to become more realistic. We rest again. Clarity does not mean simplicity. Another important aspect of prediction involves simulation. Large numerical simulations produce synthetic images based on physical laws and assumptions. These images are then compared to real ones. Agreement supports the model. disagreement guides revision. This comparison requires translating simulation output into the same observational space as the telescope data. The same limitations are applied resolution, noise, wavelength response. Only then is comparison meaningful. This step is often invisible outside technical literature, but it is central. It ensures that models are tested under the same constraints as reality. We pause and consolidate. Images are not compared to imagination. They are compared to constrained predictions. At this point, the question of realism has shifted again. Realness is no longer about whether the image looks convincing. It is about whether it can falsify expectations. This reframing resolves many surface-level debates. An image that fails to look natural may be precisely what a successful test looks like. Nature is under no obligation to match human visual preference. We rest again. Expectation is trained by evidence, not aesthetics. Now we prepare to move toward a more grounded resolution. If images are interfaces, constraints, and tests, how should they be understood by non-specialists? What does it mean, practically, to say that these images are real? Answering this does not require more technical detail. It requires consolidating what has already been rebuilt. The images are real because they are anchored in measured interaction between light and matter. They are real because they constrain models in reproducible ways. They are real because independent methods converge on compatible interpretations. They are not real in the sense of being direct views. They are not real in the sense of being complete. They are not final. This distinction stabilizes expectation without diminishing significance. With this understanding in place, we are ready to return to the opening intuition images as pictures and complete its replacement with a more durable frame that can support continued learning without collapse. That return does not add new concepts. It tightens alignment between perception and process. At this point, the original intuition about images has been stretched, corrected, and partially dismantled. What remains is not absence, but a more precise frame. To stabilize it, we need to return to the word that started the confusion: real. In everyday use, real means immediate. It means direct sensory access. It means that what we see corresponds closely to what is there. This definition works well at human scale. It fails quietly as scale increases. So we replace it. At this scale, real means constrained by measurement. It means that what is shown cannot be chosen freely. It means that independent observers, using the same data and methods, will converge on compatible representations. It means that alternative interpretations are limited and testable. Under this definition, the images from the James Webb Space Telescope are unambiguously real. They are real because the photons were detected, counted, and calibrated. They are real because the processing steps are documented and repeatable. They are real because the resulting representations constrain what the universe can be like. This definition feels less satisfying at first because it removes immediacy, but it is more durable. It does not collapse when mediation is acknowledged. We pause and restate. Reality here is not what feels direct. It is what resists arbitrary change. Now we examine a remaining source of discomfort. If images are translations, does that mean there is no privileged view? Does every representation stand on equal footing? The answer is no, and this is where intuition often overshoots in the opposite direction. Translations are constrained by fidelity to data and by purpose. Some representations preserve spatial relationships, others emphasize spectral differences. Some are optimized for human interpretation, others for quantitative analysis. These are not interchangeable, but they are not arbitrary. A representation that distorts relationships or violates physical constraints is not acceptable. It fails reproducibility. It fails consistency. It fails comparison with other data. The existence of multiple valid representations does not imply relativism. It implies dimensionality. We rest again. Multiple views do not mean multiple realities. This allows us to clarify another persistent confusion. the role of trust. Trust here is not placed in images, it is placed in process. The credibility of the image derives from the transparency of how it was produced and how it is used. This is why raw data, calibration pipelines, and analysis codes are shared. This openness is not performative, it is functional. It allows errors to be found and corrected. It allows interpretations to be challenged. The image is not a claim that must be believed. It is an artifact that must survive scrutiny. Once this is understood, skepticism becomes productive rather than corrosive. Asking how an image was made is not suspicion, it is engagement. We pause again. The correct response to these images is not acceptance or rejection, it is interrogation. Now we address a quieter intuition that often goes unnoticed, that seeing is the final step of understanding. In fact, at this scale, seeing is often the first step. Images identify where to look more closely, not what to conclude. Detailed follow-up involves spectroscopy, statistical analysis, and comparison across samples. Many of the most important results associated with the James Webb Space Telescope are not visual at all. They are numerical constraints, confidence intervals, and parameter shifts. The image initiates inquiry, it does not end it. We rest again. Seeing is a beginning, not conclusion. This brings us to a practical recalibration. When encountering a new image, the most useful question is not, is this real, but what does this representation encode, and what does it omit? This question respects both the power and the limits of the image. Encoded information includes relative brightness, spatial distribution, and wavelength-dependent structure. Omitted information includes absolute scale without context, uncertainty ranges, and alternative model fits. Knowing this prevents overinterpretation. At this stage, intuition is no longer fighting the process, it is aligned with it. Now we consider how this alignment affects future images. As new data arrives, some interpretations will change. This is not retroactive falsification, it is refinement. Earlier images were not wrong. They were incomplete under then current constraints. This distinction is critical for maintaining trust over time. Change does not imply error, it implies learning. We pause again and restate what now feels stable. The images are real, but their meaning is provisional. Provisional does not mean unreliable, it means conditional on current evidence. With this frame, we can revisit public reactions without judgment. Excitement, skepticism, and confusion all stem from mismatched intuition. When intuition is updated, these reactions settle into curiosity and patience. Now we prepare to approach the final consolidation. There are no new mechanisms to introduce. There are no hidden revelations waiting. What remains is to integrate the rebuilt intuitions into a coherent stance that can be carried forward. That stance is simple, but non-intuitive reality at this scale is not something we look at. It is something we infer under constraint. The James Webb Space Telescope images are among the most refined interfaces ever built for this purpose. They are not perfect. They are not complete. They are sufficient to advance understanding. We rest one final time before the closing movement. We understand what these images are made of. We understand what they can and cannot do. We understand why they look the way they do. With this understanding in place, returning to the opening question no longer produces tension, it produces clarity. With clarity established, we can now examine how this rebuilt intuition holds up when confronted with the most emotionally charged reactions to these images. These reactions are rarely about data. They are about expectation. They arise when people unconsciously demand that images satisfy roles they were never meant to play. One such role is proof. There is a persistent desire for images to function as final confirmation, as if seeing something settles its existence beyond dispute. At human scale, this often works. Seeing an object confirms it is there. At cosmic scale, this expectation collapses. Images from the James Webb Space Telescope do not prove theories in isolation. They participate in evidentiary chains. They strengthen some links, weaken others, and leave many unchanged. Proof emerges from convergence, not from a single visual artifact. This matters because disappointment often follows when an image does not settle a debate. But debates at this scale are not settled visually. They are narrowed incrementally. We pause and restate as images constrain. They do not conclude. Another role people implicitly assign to these images is authenticity through resemblance. If an image looks natural, it feels trustworthy. If it looks unfamiliar, it feels artificial. This reaction is understandable, but it reverses the logic of discovery. The unfamiliarity of many James Webb images is not a signal of fabrication. It is a signal that we are observing regimes the human brain did not evolve to recognize. Familiarity would be more suspicious, not less. This is another intuition to replace. Trust does not come from resemblance. It comes from consistency with measurement. We rest again. Strangeness is not a flaw. Now we address a different expectation that images should be self-explanatory. In everyday life, pictures communicate without annotation. At extreme scale, this fails. These images require context, not because they are misleading, but because they are dense. Without context, viewers may misidentify foreground and background, misread scale, or misinterpret color. This does not indicate deception. It indicates compression. The image carries more information than casual viewing can unpack. This is why explanatory captions, supplemental graphics, and accompanying data are essential. They are not just educational, they are corrective. We pause and restate. An image that requires explanation is not weaker, it is richer. Another emotionally charged reaction involves suspicion of processing. The idea that computers alter images triggers concerns about manipulation. This concern assumes that unprocessed data is more honest. At this scale, unprocessed data is not honest, it is unusable. Raw detector output contains distortions that obscure physical signals. Processing removes known biases. This increases fidelity to reality, not distance from it. The key distinction is between processing that is constrained by calibration and processing that is unconstrained. The former is required, the latter is excluded by scientific practice. We rest again. Processing is not embellishment, it is correction. Now we examine a quieter reaction, the sense that these images are somehow too much, that they overwhelm rather than inform. This reaction is cognitive, not emotional. It arises when intuition cannot find stable footing. What we have done so far is replace unstable footing with structured understanding. Once the image is seen as an interface layered, constrained. Provisional, the overload diminishes. The image becomes navigable. This is not about becoming comfortable. It is about becoming oriented. We pause and consolidate. Orientation replaces awe. Orientation replaces suspicion. With this orientation, it becomes possible to ask better questions. Instead of, is this image fake, we ask, what assumptions underlie this representation? Instead of, what am I seeing, we ask, what measurements support this? These questions align with how scientists interact with the data. They close the gap between public perception and professional practice. Now we turn to a final expectation that often remains implicit, that images should deliver meaning on their own. Meaning, however, is not embedded in photons. It emerges from interpretation within frameworks. This does not reduce significance, it clarifies it. The significance of these images lies in what they allow us to say with greater confidence and what they force us to abandon. This significance accumulates over time, across many images and analyses. We rest again. Meaning is not in the image, it is in the constraint the image imposes. At this point, all major intuition replacements are in place. We understand how the images are produced. We understand how they are interpreted. We understand their limits. What remains is not new information, but integration. Integration means holding all of this simultaneously without collapse, that the images are real, mediated, constrained, provisional, and indispensable. None of these properties cancel the others. This integrated stance is stable. It does not require constant defense. It adapts as new data arrives. We pause one final time before the conclusion. The James Webb Space Telescope images are not windows into the universe in the way our eyes provide windows into a room. They are instruments we look through in order to think. Thinking at this scale is what seeing has become. With that understanding fully in place, we are ready to return calmly to where we began, without adding anything new, and allow the opening intuition to settle into its final form. Returning to where we began does not mean repeating the opening. It means reoccupying it with a different internal structure at the start. The images felt familiar and immediate, even as we suspected that this familiarity was misleading. Now, familiarity has been replaced with orientation. When we look again at an image from the James Webb Space Telescope, the first thing that changes is what we no longer expect. We no longer expect a frozen moment. We no longer expect direct vision. We no longer expect completeness. Those expectations have been retired. In their place is a quieter understanding. This image is a record of interaction. Ancient light interacted with matter long ago. That interaction encoded information. The information travelled, changed, weakened, and finally interacted again with carefully designed instruments. What we see is the end of that chain, not its beginning. This framing is stable because it does not ask the image to do more than it can. We pause and restate. The image is not an encounter, it is an interface. Once this settles, another subtle shift occurs. The image stops feeling like an object and starts feeling like a process. It is something that happened, not something that simply exists. Every pixel represents work emission, propagation, detection, correction, translation. This awareness does not make the image heavier, it makes it intelligible. Now we examine how this affects our sense of distance. Early on, distance was introduced as scale pressure. Light travelled for spans of time that dwarf human history. That remains true. What changes is how distance is felt. Distance is no longer an abstract number or an overwhelming span. It is a condition that shapes what information survives. Distant objects are not merely farther away. They are filtered by time, expansion, and loss. The image is not showing us everything that was there. It is showing us what endured. This reframes remoteness. We are not peering across space. We are receiving remnants that made it through. We rest again. Distance is survival, not separation. This perspective also stabilizes the idea of age. We often say that these images show the universe when it was young. This is accurate, but incomplete. What we are really seeing is the universe as it appears through the narrow channel that still connects that time to now. Many things that existed then left no trace we can receive. What we see is bias toward what emits light, what emits it persistently, and what emits it in wavelengths we can detect. This bias is not a flaw. It is a condition. Recognizing it prevents overgeneralization. We pause and restate. The image is representative, not exhaustive. Now we consider how this rebuilt intuition supports long-term engagement. Future images will be sharper, deeper, and broader in coverage. They will not resolve all uncertainty. They will introduce new forms of it. This is not a problem to be solved. It is a dynamic to be managed. With the correct frame, new complexity does not destabilize understanding. It extends it. This is why the work continues calmly rather than dramatically. Each image adds constraints. Some questions close, others open. The balance shifts gradually. We rest again. Progress here is incremental, not revelatory. Another benefit of this frame is that it dissolves the false tension between scientific and public images. The public image is not a diluted version of science. It is a different representation serving a different cognitive role. When understood as such, It complements rather than competes with technical analysis. This complementarity matters. Without public images, the scale and significance of the work remain abstract. Without scientific rigor, images become spectacle. Together, they form a functional loop. We pause and consolidate. Representation and analysis are partners, not rivals. At this point, nothing essential remains unaddressed. There are no hidden layers waiting to be exposed. The remaining work is maintenance, keeping intuition aligned as new data arrives. This maintenance involves repeating what has been learned, because intuition regresses under pressure. It defaults to immediacy, simplicity, and completeness. These defaults must be continually countered. This is why explanations recur, not because the audience is slow, but because the scale is hostile to stable understanding. We rest again. Repetition here is reinforcement, not redundancy. Now we prepare for the final return. The opening sentence promised that our intuition about these images was incomplete. That promise has been fulfilled, not by adding facts, but by replacing assumptions. What remains is not a conclusion, but a stance. The stance is this when confronted with an image from the James Webb Space Telescope. We do not ask whether it is real in the everyday sense. We ask how it is real in the only sense that applies here through measurement, constraint, and inference. This stance does not end curiosity, it channels it. We pause one last time before closing. The images have not become smaller or less impressive. They have become clearer in their role. They are tools for thinking at scales where direct experience fails. With that clarity, there is nothing left to resolve. There is only continued observation, continued testing, and continued refinement. The universe does not become simpler as we look deeper. Our understanding becomes more disciplined. And that discipline is what allows us to remain oriented inside a reality that exceeds human intuition. Tonight, we began with something that looked familiar: images that resemble photographs, scenes that seem captured, moments that feel preserved. That familiarity was the starting point, and it was also the problem. What we have done since is not to strip that familiarity away, but to place it where it belongs. Now, when we return to those images, they no longer ask to be believed, they ask to be understood. We understand that what we're seeing did not arrive as a picture. It arrived as light that survived an immense journey, altered by expansion, filtered by matter, and thinned by distance. It arrived not all at once, not from a single moment, and not in a form our senses could ever receive on their own. We understand that instruments replaced our eyes, not to extend them, but to stand in for them where extension fails. We understand that detectors counted interactions, not scenes, and that those counts were assembled, corrected, and translated into forms that human cognition can work with. This understanding does not make the images less real, it makes their reality precise. We pause and restate the central frame one last time. These images are not windows, they are interfaces, they are not snapshots, they are summaries of constraint, they are not the universe as it is, they are the universe as it can be known from here. Once this is held steadily, there is no remaining tension. The colours no longer feel suspect, because we know what they encode. The shapes no longer feel deceptive, because we know how they are inferred. The absence of certain details no longer feels like omission, because we know where physics draws boundaries. Nothing is hidden, nothing is overstated. We also understand something quieter but more important. The work these images do is not primarily visual. The visual form is a surface. Beneath it is a disciplined process that limits interpretation rather than amplifying it. Every image is a narrowing of possibility, a reduction of what the universe could be like. This is not how intuition expects truth to behave. Intuition expects revelation. Here, truth behaves as elimination. We rest again. Understanding at this scale is subtractive. With this frame, the images settle into their proper role. They are not endpoints. They are working objects. They are places where models meet resistance, where expectations encounter constraint, where certainty grows not by affirmation, but by survival. The universe did not become visible because of these images. It became testable in regimes that were previously unreachable. This is why the work continues without finality. Each image participates in an ongoing process that has no natural stopping point. Better data refines models. Refined models guide new observations. The cycle tightens. There is no moment where the universe is finally seen as it truly is. There is only increasing alignment between what is inferred and what is constrained. We pause one last time to anchor this. At the beginning, we were tempted to ask whether these images are real. Now, that question no longer fits. Reality here is not a visual quality. It is a property of process. It is the resistance of the data to arbitrary interpretation. It is the convergence of independent analysis. It is the survival of explanation under repeated testing. By that measure, these images are among the most real representations humanity has ever produced. They are real not because they resemble what we expect, but because they force our expectations to change. This is the stable position we end with. We live in a universe that does not present itself directly at extreme scale. We do not see it as it is. We infer it through carefully constructed interfaces that respect physical law and cognitive limitation. The James Webb Space Telescope images are such interfaces. They are not illusions. They are not art. They are not guesses. They are disciplined translations of what has endured long enough, travelled far enough, and interacted gently enough to reach us at all. With this understanding, there is nothing left to defend and nothing left to debunk. There is only continued work. This is the reality we live in. We understand it better now, and the work continues.